Okay.
Thank
All
you.
right. Well, thanks very much. Sorry for the kerfuffle with it turned out to be Dropbox, which was a fail. Okay, so what I'm going to talk about is data optimization for the cloud. This is like yet another cloud presentation. Um, um, and this comes from the NASA Earth Data Cloud Services Group. Patrick Quinn is the co-author of this presentation. And this work was sponsored by NASA and under a Raytheon contract. Oops. Okay, so that's a bit of a fail. So okay, so review. What do we mean by cloud optimized? Can you guys hear me? Okay.
Yes.
Okay, great. So what do we mean by cloud optimized, and why do we care? And so I've got a file location. How do I get data that I care about from it? So what do? Well, you locate parts of the file that you need to read, and then you read the parts of the file, right? And then you have to translate the data. Usually that means decompressing it, throwing away extra things that I had to read but didn't really want. And so when you have files on a hard drive, there's a couple of things that are essential characteristics of those devices. And the number one is that the latency is really low, really low, especially for solid state drives. And the throughput is really very high, but unfortunately parallelism is low. So you have this set of three features, this triumvirate that sort of gang up on you. And what they do is they force formats to favor many small reads for getting only the necessary data, because this parallelism is low. You can't really take advantage of core counts and stuff like that. But when you move to the cloud, the sort of, you have a different triumvirate gang up against you. Now latency is really high, 70 milliseconds or more for S3. So 70 milliseconds is really conservative. If you have to go, if you're involved in a more complex cloud environment that involves lots of authorization and authentication, 70 milliseconds, you'll never get there. It'll always be longer. Throughput, though, is exceptionally high once you establish communications, like 25 gigabits a second. And the other thing is that cloud data stores, or web object stores, as another term that you'll see, parallelism is extremely high because those systems were designed to serve hundreds of thousands or millions of users simultaneously. Not necessarily all working with exactly the same data, but they're designed for extremely high use. So this changes the optimal way of organizing data. It emphasizes fewer reads, even when that means fetching a whole lot of extra data only to throw it away. And also, too many reads make it faster to download the whole process, the whole file, and process it offline. In other words, if you have to do too much I/O with this thing, if you have to go back to it too many times, you might as well just get the whole file, move it to a spinning disk, and work with it there. So that's kind of the background, okay? And that's where we started with this work. So now we're going to talk about OPeNDAP in the cloud and this technique that we developed called DMR++. So DMR++ is almost, it's kind of a meaningless name. It stands for Dataset Metadata Response. And the plus means we augmented it with the information about where each chunk lives in a particular data file. It doesn't actually have to be an HDF5 file, but so far we've only actually implemented this for HDF5 files and also files written with the NetCDF4 API, which you guys all probably realize is an HDF5 file. So this all started with some experimental work to ask the question, what are the different possible architectures that we could construct that would enable us to build OPeNDAP in the cloud? And so let's go over those now and talk about the ways that each one of them can actually be in its own right an optimal solution. And then we chose one of those three to go more with, and so we'll talk about that in a bit. The first architecture is essentially our baseline. And in this architecture, we have data in S3. And what we do is whenever we want to read from this data, we pull it into a cache. We don't bother thinking about whether it's the right thing to do or not. We just pull it into the cache, We have it in a spinning disk, and we work with it there. In one deployment, we used Elastic EBS. I forget exactly what that stands for now, Elastic Block Store. And we've also used EFS, which is their shareable version. And we've used other kinds of Amazon spinning disk clones. We've also replicated this architecture in a couple of other cloud environments. The thing is that this is optimal in the case where you have to do a whole lot of IO operations on the file. Large number of operations, and this wins. Another architecture that works well is to take an HDF5 file and view it as having a whole bunch of shards, but they're all inside the file, nicely packaged. And you do this range get to read parts of them. And that's become a really popular architecture. We're going to talk a lot more about that, assuming that I have time. And then the third architecture is to actually shard the files or shred the files. And so you can take a data file and rip it up into a whole bunch of pieces and associate an S3 object, which is referenced by a URL, with each one of those pieces. So if you've got 100,000 chunks in an HDF5 file, you might break it into 100,000 objects. There are some pluses and minuses there, but it turns out that its actual performance in practice is very similar to the second architecture. So let's compare these two. So this is like my anti-Edward Tufte slide. It only contains words. So like I said, transferring the whole file can be the fastest way to get data, even when you only want a small amount of that data, if you have to go back and forth to the file a whole bunch of times. Virtual sharding preserves the original data file, which is also the case in architecture 1, and it also allows subsetting in place. But to be performant, the virtual sharding has to be heavily optimized. And if you've done any device driver work, you suddenly realize that your data server now has a whole lot of code that looks a lot like a device driver living inside it. The other thing is that in order for this virtual sharding technique to work, it's essentially a data-driven algorithm, and that data has to be harvested beforehand. So, well, actually technically doesn't, but in practice, it really does. So that means that all of the data that will be used with this virtual sharding technique, this DRM++ technique, they have to go through an ingest process that produces a metadata file. And that metadata file is separate nominally from the HDF5 file in our case. True sharding, which is actually the solution that Czar uses, well, obviously that breaks it apart, right? So this has the potential to reduce the data size, because you can have, if you have chunks that are just fill values, you can just record the chunk once and you can have many, many object pointers referencing to it. So that's kind of cool. But that's kind of a sideline. An issue with this architecture is that it alters the underlying data file. And there may be reasons that you don't want to do that. It would be really nice to not have to essentially reformat all of your data. So for DMR++, here's how you use it. First, you have to build this DMR++ metadata file. That's the pre-processing data ingest phase. And you have to choose a fair number of options that alter the appearance of the file. Now, this talk was originally given at the summer ESIP meeting, or most of it was. And there I was really talking about what we do for DMR++ inside NASA. And they want their HDF5 data to look like they're CF compliant, even though many of those data sets were designed years before CF compliance really became a big thing. And so because of that, we modify those files. We oftentimes add data that are missing, like latitude and longitude vectors and things like that. And we modify attribute values as well. So the correct options have to be given when these metadata files are built up. But it's important to know that this additional metadata file doesn't just provide the mapping into the HDF5 file that tells you where the chunks are. It also alters the way the information is presented. Right now, those documents are XML, which has its pluses and minuses. When we store the metadata in S3, so there's a bit of latency to pull it off. And for a typical NASA file, these things can be 100 megabytes. They can be pretty large. Also, I noticed the timer says 4:27. Is that the total time or the time till questions?
That should be till questions.
Oh, okay, great. So, because I'm close to being done here, so we should have plenty of time for questions. So in this mode, how does the data access go? So the server reads this byte offset and the size number, and then it just issues a range get to grab the data. This is the part of writing this stuff that looks a lot like a device driver. This is exactly what device drivers do to get data off disks. And just like that, you constantly have to check for errors. And many times you do get errors back from S3. It happens not quite 1% of the time, but more than 0.1% of the time. And the error is totally opaque. It just says this failed. And the fix is try it again. And the other thing that you have to do in order to avoid accesses that are statistically far longer than the average is that if the requests start taking more than like 2 standard deviations beyond the average, just stop it and start over again. So your device driver, your code has to implement these sort of heuristic things that say, if this device is not behaving the way I expect it to, stop what I'm doing now and start over again, start up again. But again, in order to do that, you can't run these accesses in series. You just can't do that. So you have to run them in parallel. That's the only way to get the latency to disappear or to be minimized. So once we pull the chunks back, then the chunks have to be assembled to get the actual data value. So there's the optimization of using parallel reads. And there's the notion that you want to, of course, decompress the chunks in parallel. But there's one more thing that you have to do if you want to work with the original files and not re-chunk them. Because remember, I said at the beginning that these high latency devices, they really favor large transfers. So that means large chunks. So what we do is we combine adjacent chunks into what we call superchunks. And we may transfer 1,000 chunks in a single S3 request. We pull that into memory, but then we know that there's actually 1,000 chunks there. So then we run a large number of parallel processes to work with each of those chunks individually to decompress them, right? Because the compression is per chunk. And same thing with things like Fletcher 32 and whatnot. So that turns out to be a really important optimization. Other people have come across this same thing. You know, at this point, a fair number of people have been working with this range get technology. And I think other people have come to the same conclusion. So some other things that happen when you start looking at these data this way, it becomes fairly easy to build aggregations across multiple files. In effect, it's not any different than that architecture 3 where the file was sharded, right? Now you put in your metadata pointers to things that are spread across many different objects. It's just that some of those objects are in one file and some of the objects are in another file. The other thing to realize is that this same technique can be used on spinning disks, and it can actually be very, very fast. If you don't need to do a lot of interrogation for attributes and things like that, this can be a very fast way to get data off a spinning disk. This also could, in theory, make access sort of format independent. But we haven't actually tried that very much. We've only done this with HDF5. So at this point, I have questions, and I should point out that this work was done. I'm technically the president of OPeNDAP, but in this work, my role is an EED2 software engineer. And so, and I'm working with the EOS DIS group. So any questions?
Thanks, James. And we have time for a few questions.
Hey, James, it's John. I was curious, one challenge I think is kind of extracting those chunk locations, right? So I found it's been a little slow, right? For these large files, they may have 1 million chunks, and the H5 library has a function to extract the chunk location, but you had to call it per chunk. So that can take some time to process a large file. So have you any special ideas on dealing with that? Or has that been a problem for OPeNDAP?
So we actually have come across files with 1 million chunks. We have dealt with that. And that's where we get these huge metadata files, XML files that are hundreds of megabytes. But we're pre-processing the data. So we don't use the chunk information on the fly. Well, okay, wait a second, that didn't come out quite right. We don't query for the chunk information on the fly. What we do instead is we pre-process the data. So we build up all of this information and we store it in a single XML document. And then it's that XML document that we query. Your mileage may vary depending on whether you think XML is something you can get to quickly or not, but so I don't know if it's actually faster than the HDF5 API, to tell you the truth, but and
yeah, even offline, I found it'd be a bit of a burden.
Okay.
Large files.
Yeah. So one of the things that we've come across is that processing this XML document that contains all of this metadata, first of all, it's more than half chunk information in every single case we've looked at. Okay, so that's an issue. And secondly, it can take us 30 seconds, 40 seconds, a minute to fully process these files. So what we've started to do, what we're working on now, is keeping it in the XML form, because that's turned out to be useful for other reasons, but selectively parsing it. Parsing just like building up a DOM representation, but not actually understanding what it contains, and then going in and cherry picking information from it. And that turns out to be quite fast. So that's what we wound up doing. And thus only reading the chunk information that we need at the time when we need it. But nonetheless, we do build up the XML representation offline in a pre-processing step. And that can take as long as we want.
Right. One thing I do for storing the chunk information in HSDS is I have data sets that are data sets of chunk locations. So now you have all your chunk locations in a compact format. So when you're accessing a chunk, you have this indirection. You go to a data set to get the chunk locations, to get the chunks, to get the data. And that's worked out pretty well, even though it's a little bit head spinning to think about it.
Interesting.
I would like to chime in. The latest versions of HDF5 has much better optimized chunk iterate function. It works much faster. So if you're not using latest 1.12 or 1.10.8 that will come in, try to use it. It should give you pretty good performance.
Okay, well, that's really good to know. Yeah, definitely. Okay.
And so a contribution from community, that was great.
Thanks. Are there other questions?
I have one more question if someone else does. I'm curious, James, is EOS thinking of having DMR++ as like a standard sort?
I don't know if they've pushed it to a standard, but it is a thing that we're doing. Yes. So yeah. I mean, they're going to try to make all of the HDF5 data that they push to the cloud accessible with OPeNDAP. And right now, unless there's a shadow OPeNDAP group I don't know about. It's going to be done with DMR++. So yeah.
No, but I'm thinking like have DMR plus files in the S3 buckets that
They are there, yeah. Yeah, they will be there. But right now they're not actually indexed as such in CMR. You just sort of have to know that there's this, when you look up something in CMR, you see, oh, there's this OPeNDAP related URL. If it points into S3, then if you change the extension, or maybe it's add the extension .dmrpp on the end of it, you'll get that DMR++ XML file.
Okay, cool.
All right.
Yeah.
Thank you so much.
Yeah.
We,
Thanks.
Thank you, James. And we're moving on to the next